So now that we've had a chance to kind of open up our conversation about covalent bonding and that we have reviewed how to draw Lewis dot structures, and in particular, Lewis dot structures that display resonance, it's time to discuss this weird topic called formal charge. Now, formal charge is a way of deciphering which of our resonance structures is the best or most stable. So again, formal charges are assigned to each atom on the inside of a Lewis structure. And they kind of talk about how much stress each one of those atoms is undergoing. Now, an atom is happiest when it has exactly the correct number of protons, neutrons, and electrons. In other words, its actual charge is as close to zero as possible. But when we're undergoing covalent bonding, we know that some of our electrons are going to end up being shared. And that bonding may actually limit an atom's individual ability to actually touch and have contact with that 100% perfect number of electrons. Now, although this does not necessarily create an official charge like we see in ionic bonding, because the electron is officially either ripped away or donated to each atom, it does kind of create some sort of a weird imbalance on the inside of the structure. It's not really a charge, but it's a lack of an ability to command your own electrons. So it feels a lot like a charge. That's why we call it formal charge. Let's take a look at this lovely Lewis dot structure. Now, this is one that should seem familiar. This is the cyanide polyatomic ion. And formal charge actually has an equation to it. So we're going to take the number of valence electrons that's officially assigned to the atom. That's a lot like calculating your A in S equals N minus A. And then we're going to subtract the number of electrons the atom actually touches. Now, you might be wondering what counts as an electron that it actually touches. Well, that would include any lone pair that's assigned to that atom. That's going to count as 2 electrons. And also a bond. Now, through a bond, we know that an atom can have donated 1 electron to that bond. 2 electrons total make a bond, but the other electron came from another atom. So through a bond, that atom can really only claim 1 electron. Let's do a sample calculation, say for this carbon that's in this structure. So we're going to start off with the number of valence electrons that's assigned to carbon. That would be 4. And now we're going to subtract out the number of electrons it touches. So first of all, it has a lone pair, so that's going to count as 2. And then it also touches these 3 bonds. So that counts as a further 3 electrons that it can touch. So carbon's formal charge would come out to be a -1. So it's actually being able to command more electrons than what it came into this structure with. And again, that's creating a little bit of imbalance and maybe a little lack of stability. Well, why don't we go and do the same process for the nitrogen? So again, nitrogen has 5 valence electrons. It is touching a lone pair, so we're going to count it in as 2 that it touches. And it also touches these 3 bonds as well. That's a further 3 electrons. So overall, nitrogen's formal charge here is 0. Now take a look at this, which is kind of interesting. So the formal charge of carbon is going to be -1, and the formal charge of nitrogen is going to be 0. What is a nice thing to keep in mind as you're moving forward, a nice way of self-checking, is that if you add up the formal charges of all of the atoms on the inside of the structure, they should always equal the overall charge. So if we add carbon's -1, nitrogen's 0, that does in fact equal the -1 charge of cyanide. Another tip or trick is to try and keep your formal charges as close to 0 as possible. Again, they want to have command over that perfect number of electrons. So the closer to 0 that you can actually get those numbers means that you're the closest to that perfect balance. And if you do have to have charges, like if they're completely unavoidable, then it would be best to try and keep your negative formal charges on more electronegative atoms and to keep your positive charges on more electropositive atoms. And I know that's kind of an outdated term. I guess it would be on your less electronegative atoms. So something that's closer to francium on the periodic table. Okay, and again, just one more time, your formal charges should always equal the overall charge of this structure. It's a great way of being able to check your work, because if your formal charges add up to something other than your overall charge, you know that you've made a mathematical error somewhere. Now let's take a look at a very specific example. Now we opened up this whole section here by saying that formal charge was a way of deciphering whether or not you have a good resonance structure or a weak resonance structure. So I have three resonance structures up at the top here for the thiocyanate ion. We're going to go through and calculate the formal charges of every atom in this structure. Starting here with the sulfur all the way over to the left-hand side of the screen. Sulfur has 6 valence electrons, but here is touching 7, so his formal charge is a -1. The carbon in the center has 4 valence electrons and is touching 4, so his charge would be 0. And the nitrogen has 5 valence electrons and is touching 5, so his charge would also be 0. To the center structure, the sulfur to the left-hand side of the middle structure has 6 and is touching 6, so his overall charge would be 0. The carbon in the center, the same thing, has 4 but is touching 4, so his charge is 0. The nitrogen to the right-hand side has 5 but is touching 6, so his charge would be a -1. Final structure. The sulfur to the left-hand side of the final structure has 6, but this time is touching 5. So his now charge is going to be a +1. The carbon to the center has 4 and is touching 4, formal charge of 0. And the nitrogen all the way over to the right-hand side has 5, but this time is touching 7. So it has 3 lone pairs, which counts as 6, and the bond gets you up to the 7th. 5 minus 7 is formal charge of -2. That's pretty extreme. Okay, so let's decipher which structure here may actually be the best. A couple reminders when we're going in to decide is that you want your overall charges as close to 0 as possible. But if charges are unavoidable, make sure that the negative charges are on the more electronegative atoms and that the positive charges are on the least electronegative atoms. Sometimes I say electropositive. Again, that's kind of an outdated term. Okay, so let's decipher these structures. Let's kind of focus on this one all the way over here to the right first. What I notice is that those charges are further away from 0 than the other structures. So this is not going to be the best structure. I would eliminate this one almost right out from the gate, so to speak, as being a good structure. So then let's take a look at the other two. They're kind of neck and neck at this point. They both have 2 zeros and 1 -1. And notice in all of the structures, all of the individual formal charges add up to that overall charge of a -1. But these two structures would be better because their charges are closer to 0. But which one is even best? So again, they all have similar formal charges, but what I do notice is that in the orange circled structure, the -1 is on the more electronegative atom. Sulfur is slightly more electronegative than the nitrogen is. So in the purple structure, that -1 is on the less electronegative atom. And in my mind, that means that the orange structure is in fact your best choice. So the best choice of resonance structures for the thiocyanate ion is going to be the structure all the way to the left-hand side.